Jai Hind students, we are discussing about the various antennas that are used for the satellite. In the previous lectures, we studied about various subsystems of the satellite that are AOCS, TTCM and power subsystem. Till now we studied these three. AOCS stand for the attitude and orbital control subsystem. TTCM stand for the telemetry, tracking and command and monitoring subsystem. And combinedly, they both will work for monitoring the health of the satellite, to monitoring the attitude and orbital location of the satellite, and also they maintain the satellite in its location. The third subsystem was power subsystem, which is used for the power requirement of a satellite, and basically solar panels and batteries are used for the rechargeable batteries are used for the power requirement of the satellite. Then this antenna subsystem will came into the picture because a satellite subsystems, when we are discussing the satellite subsystem, communication subsystem is mainly the heart of a satellite. But when we talk in terms of weight and the other parameters, this is the smallest one subsystem of a satellite. But this play the main important role of the communication. And actually all the revenue which is generated by a satellite is coming from this communication subsystem. And for communication subsystem, you have to transmit or receive the data from the earth station. That's why antenna is required. So antenna subsystem came into the picture. In previous lecture, we talk about the antenna definition and the wire antenna. There we discuss about the dipole antenna, and today we are going towards the antenna array and the remaining two, horn and the reflector antenna. Antenna array. Basically, when you are talking a dipole antenna, just take as dipole antenna, length lambda by 2. Its directivity and gain are fixed. But whenever for a specific requirement you want to increase the directivity or gain of a antenna, then you use a group of antenna connected and arranged in a regular structure to form a single antenna that is able to produce radiation pattern not produced by the individual antenna. So this antenna array is a group of isotropic or similar antennas of electromagnetic frequency and energy, and they provide a solution to the problem caused by the single antennas, means the low directivity and gain can be increased by a group of antenna. For instance, the dipole antenna allow better control of direction than an isotropic antenna, but as the length of the dipole increases, control direction may decreases. So for the more control and flexibility, you can use a group of antenna that can be easily regained from beam direction with a multiple radiator arrangement. So this antenna array is actually required for the beam requirement, as your earth is a sphere, and to cover its various regions through the spotlights type structure or spotlight light type radiation pattern, then you require these antenna arrays. Also, you can change the polarization and other parameter also through this. So basically, these antenna array are generally used for the to increase the overall gain. Also, they provide diversity reception. They cancel out the difference from a set of various direction, and also steer the array so that it is most sensitive in a particular direction. Means I am told, as I told you, if you want to cover a specific direction through a beam, it means it is most sensitive. It will make the antenna array in such a way that it will most sensitive to a particular direction. Also, the direction of arrival of the incoming signal, means these antenna array not only used for the transmission purpose, it can also be used for the receiving purpose. So also they help to maximize the signal to noise ratio, signal to interference plus noise ratio. It means these antenna array are combinedly play a important role in the satellite beam formation. Then there are two types of basically antenna array. First one is parasitic and second one is driven array antenna. Parasitic or driven array antenna you can understand by this example of Yagi-Uda antenna. As you already studied this in your antenna subject, that Yagi-Uda antenna, actually you have multiple elements arranged across a axis. In this Yagi-Uda antenna, you can see that the feeding is applied to this, folded dipole antenna, and these all other elements are used to increase the directivity. These all parameters are called directors. These all are called directors, and this is called reflector. This is called reflector. So you can easily identify that here this element is driven element, but these are this is the driver element and these are the driven element. So when we are talking about the parasitic array, this is used for controlling radar and various other narrow beam such as the microwave communication system. But when we are talking about the driven array antenna, radiating elements are connected to an energy source and have less loss when compared to parasitic array, but still maintain the narrow beam characteristics are used as search radar antenna, where narrow beam are less critical when compared to low losses. Here we are talking about the radar part, but in the satellite that same application is applied for the various beam. Means in parasitic array all the antennas are just dependent on the other element for the feeding. In the driven array they are derived by the individual element. Then these are the various type of antenna array present that are used by the satellite, that is such as collinear array, broadside array, end fire array, parasitic, Yagi-Uda, log periodic, turnstile array. The main arrays are broadside and end fire, because in both broadside and end fire the only difference is we apply the both arrays, all the element of the antenna in broadside case in phase, but in the end fire case the magnitude of the applied voltage is out of phase, or we can say that there is a phase difference between two consecutive elements feeding. Similarly, there is a collinear array or other elements are also there. Then these are the various types of antenna array used by the satellite systems, such as bow tie antenna, log periodic antenna, and this is the Yagiuda antenna that is used at the earth station side, not on the satellite. So basically an array widely used as a base station antenna for mobile communication. Yagiuda is used for the TV, log periodic is used for the TV with the wider bandwidth. Broadcasting means for the specific satellite application, broadcasting and beamforming, naval using optical phased array are used. Radio frequency identification, weather research, missile guidance and fire radar aircrafts, these all systems are using the antenna arrays. Then the next, microwave antenna. There are various type of microwave antennas are present, in which horn antenna and parabolic antenna are used for satellite communication. Now what is that horn antenna? Actually, I told you in the previous lecture, if a transmission line is widened at the end and if it will be fed by some electromagnetic energy, then at this wider end it will radiated in such a way in the outer atmosphere. That same pattern will be used for the horn antenna construction. By this diagram you can easily identify this. Basically, when we are talking about EM waves have E and H field, electric field and magnetic field. Both fields are perpendicular to each other and they are creating E plane and H plane. When we are talking about, when we are talking about these EM waves, construction of horn antenna, you have two planes, E plane and H plane. So when you are taking a waveguide, actually for here we are using waveguide for the system, and as the satellite antennas are working in microwave range, because we are basically using for C, Ku and Ka bands. For microwave communication we use waveguides. That waveguide may be a rectangular waveguide or a circular waveguide. When we are talking about the rectangular waveguide, this wave also have two planes. One is E plane and second one is H plane as per the electromagnetic wave orientation. So if you widen this, the opening of the waveguide at the end in both planes equally, then it will become a pyramidal horn antenna. If you only widen it in the E plane, then it will become E plane horn antenna, or when you widen it in H plane, it will become H plane horn antenna. So basically it is used for microwave communication. So they are very popular for the UHF, more than 300 megahertz to 3 gigahertz and higher frequencies. They often have a directional radiation pattern with a high antenna gain, and that can range up to 25 dB in some cases, with 10 to 20 dB being typical. Means 10 to 20 dB is normally, but 25 dB is also in some cases. Horn antenna also have a wide impedance bandwidth, implying that the input's impedance is slowly varying over a wide frequency range. The gain of horn antenna also increases as the frequency of the operation is increased. And also because of the size of the horn aperture, it is always measured in wavelength. A higher frequency has a smaller wavelength gain. It means for the higher frequency regions, you have a small horn structure. That is also very useful for the satellite, because their space, weight and all the parameters are playing an important role in the construction of the satellite. So horn antenna has a fixed physical size, its aperture is more wavelength across the higher frequency, and also horn antenna have very little losses, so the directivity of an horn is equal to its gain. Then this is about horn antenna. Now parabolic reflector antenna. When we are talking about the parabolic reflector antenna, this is the structure of parabolic reflector. In a parabolic reflector, there are two parts. First one is primary element. This one is the primary element, and this one is the secondary element. Actually, parabolic reflector antenna work on the principle of parabola geometry. As you know that parabola have a focus, and if any rays are coming parallel to the axis of the parabola, then after reflecting back from the parabola circumference, it will centered on the focus. And similarly, if any rays are coming from the focus, they will become parallel to the axis after reflecting from the parabola. That same concept is used in the antenna structure of parabolic reflector antenna, and these parabolic reflector antenna create a very sharp beam as this direction pattern. You can see that there is a very sharp beam as per the direction pattern of the parabolic reflector antenna. So you can see here one point very clearly, that reflector antennas are utilize the fact that EM wave can be reflected to a focal point using a metal plate. So basically there are two forms, that are corner reflector or parabolic reflector. So it should be pointed out that reflector itself is not that antenna, and therefore some form of the conventional antenna placed as at the focal point of the reflector, such as monopole. Means you can identify here one point. A parabolic reflector antenna have two parts. First one is primary part and second one is secondary part is reflector part. When we are talking about the secondary part, you can see here, this is a metal plate which is only reflecting or collecting the electromagnetic waves. But the feeding or collecting the waves is done by this primary part. This primary part is somehow taken as per the requirement. It may be a horn antenna, it may be a monopole antenna, it may be a dipole antenna. Means parabolic reflector antenna is a combination of two antennas, you can say that. So this is the parabolic reflector antenna. Now the parabolic reflector typically have a very high gain of 30 to 40 dB and a low cross polarization. It means you cannot create multiple beams through a single parabola. So they also have a reasonable bandwidth, with the fractional bandwidth being at least 5% on commercially available models, and can be very wideband in the case of used dishes. Also, the smaller dishes antenna typically operate somewhere between 2 to 28 GHz. In your dish TV, you are using the parabolic reflector antenna. The large dishes can operate in the VHF range of 30 to 300 MHz, but typically need to be extremely large at this operating band. That's why at the earth station we have very large parabolic reflector antenna because of this VHF region. This is the, as discussed earlier, this is the radiation pattern of the parabolic reflector antenna, and as you can see, it is quite sharp. Then these all are the basic antenna used for the satellite. But when we are talking about satellite communication, some deep space missions or the satellite which is sent for the other planets of our solar system are also there. For that type of condition, when you required very long distance communication, that helical or helix antenna came into the picture. Basically, this helical antenna is a hybrid of two simple radiating element. One is the dipole and the other is the loop antenna. How it will become? You can see that this is the helix or helical antenna structure. You can see that it is just like a spring structure. In this is the ground plane. This is the radiation part, and you can see that this is a group of helical antenna, means it is a helical antenna array. So if you take this example, the diagram, this is the ground plane and these are the turns. If you make this spacing between two turns equal to 0, it will become this. This is the loop antenna. Or if you make this alpha angle, that angle which is creating the loops, if you make this alpha angle 0, it will become a straight line, means it will become a dipole antenna. So helical antenna become a linear antenna when its diameter approaches 0 or pitch angle goes to 90. On the other hand, a helix of fixed diameter can be seen as a loop antenna when the spacing between the turn vanishes. So here, as I told you, 0 degree on that, basically this angle is related to this angle is called about the 90 degree and this is about the 0 degree. Then it will become the dipole. So this helical antenna can work in two modes. One is normal mode and second one is axial mode. Means when this helical antenna will work in normal mode, it will work like a dipole antenna. But when it will work in axial mode, it will give this type of highly directional radiation pattern. So this is helical antenna all about. So when we are talking about this is a 3D diagram of the helical antenna in the axial, normal mode and the axial mode. You can see this. So when we are talking about the satellite antennas combinedly, you can easily identify one point that mainly the bands are KU, C, KA, and for these bands we have these wire antennas, parabolic reflector antennas, horn antennas, antenna array or phased array antennas to create the beam. That all are as per the requirement. So this is all about the antenna subsystem part of a satellite. In the next lecture, we will discuss about the heart of a satellite subsystem, that is called communication subsystem, that is called transponder. So till the next lecture, thank you.